Hi, my name is Caroline Steer, and this is my report for Lab 4, Faraday's Law for Physics 2212. In this lab, I dropped a magnet through a tube of aluminum foil. The goals of this lab are to observe and collect data from that experiment, create a computational model of the experiment using GlowScript, and then to compare the results. A preview of the results is that the measured average time the magnet was in the tube was 1.296 seconds, and the computational model calculated the time to be 1.21 seconds. Before starting the lab, there are a few important physics concepts to know. First, like the name of the lab, Faraday's law is a magnetic flux that changes in time that creates a non-Coulomb electric field that generates an EMF. The minus sign in Faraday's law is Lenz's law because nature abhors a change in flux. Next is Newton's second law of motion, saying that force is equal to mass times acceleration, and the equations that can be derived from that. Lastly is the Biot-Savart law, which states that a steady current produces a magnetic field with the strength varying depending on distance and the current. Jumping into the experiment. The system is the magnet, and the surroundings are the aluminum foil tube and everything else. The initial conditions assumed in this lab are that the magnet is acting like a magnetic dipole, and the only two forces acting on the magnet are magnetic and gravitational. With that being said, I found the north pole of the magnet using a magnetometer on my phone. I then dropped the magnet down the aluminum foil tube 5 times to find the average time the magnet was in the tube, and that was 1.296 seconds. Here are some snippets of code from the computational model on GlowScript. I initialized the tube of aluminum foil by measuring the length of the tube, width of the foil, and the inner radius. Then, I calculated B dipole. Next, I made a function to calculate dF over dt, starting with the radius, distance traveled by the magnet, and the speed. Then, the typical B field at each ring was calculated. I then put the magnetic force on the magnet in vector form. From there, I calculated the net force and updated the magnet's velocity and position using Newton's second law. Here is the result from the computational model. The graph shows the velocity of the falling magnet over time, with the time in the tube being 1.21 seconds. Moving on to the results of the experiment. The average time I measured that the magnet was in the tube was 1.296 seconds. The computational model calculated the magnet's time in the tube to be 1.21 seconds. These two values are pretty close, but there could have been a few errors that caused the difference. First, my reaction time replaying the videos of the magnet falling could have been slightly delayed. Additionally, there could have been outside forces acting on the magnet that were not accounted for in the computational model. Lastly, the measurements of the aluminum foil tube may have not been exactly accurate. Now answering some additional questions. If the resistivity of the conductor were reduced as close as possible to zero, the magnetic force would increase and the induced current would increase. This would change the dynamics of the falling magnet because the magnet would fall slower. If holes or slots were cut into the tube, there would be slightly less aluminum foil, causing the magnetic force and induced current to decrease. This would also cause the magnet to fall quicker. Thanks for watching.